In the last video, we looked at an introduction to stationary points. In this video, we're going to work through a range of questions where we find stationary points and determine their nature. Let's just do a bit of revision from the last video. We had three different types of stationary points. We had a minimum point, a maximum point, and a point of inflection. For all of these, we could say that dy dx or f dash of x was 0. So the gradient function was 0. So all of those now hold true. So let's just put these in. That's something we learned in the last video. When we looked at the second derivative and we had f double dash of x or d2y by dx squared, for a minimum that value was greater than 0. If we had now a maximum, it was less than 0. And then when we had a point of inflection, the second derivative didn't tell us about the behaviour of a function and it gave us a value of 0. When we went ahead and took the third derivative, f triple dash of x, or d3y by dx cubed, for a point of inflection, we had now a value that wasn't 0. So that's what we looked at in the last video. We also looked at simply substituting in values close to the stationary point to establish whether that was a point of inflection. So with a minimum, we can see to the left of that minimum point, we have a negative gradient, then we have a positive gradient. A maximum to the left, we have a positive, to the right, a negative, and a point of inflection, the gradient will be the same either side. So let's go ahead and work through a range of questions looking at stationary points. In question 6, we're asked to find the coordinates of any stationary points for each of the following functions and determine their nature. So in A, we've got f of x is equal to x squared plus 4x. This is a quadratic equation. With a quadratic, we can either use differentiation or we can complete the square. As this unit's on differentiation, I'm going to simply use that particular method. So in all questions, I'm going to put now for stationary point for SP, f dashed of x will be equal to 0. If this was y as a function of x, we could say now that dy dx would be equal to 0 if we had now y is equal to some function of x. So let's look at this now. What we're going to do is write f dashed of x. F dashed of x for this one right here, well that's simply going to give me 2x plus 4. So solving this by setting it equal to 0 for the stationary point, 2x plus 4 is equal to 0. So we can see that x is equal to negative 2. This gives me the x coordinate. All I need to do to find the y coordinate is simply substitute in. So y is going to be equal to negative 2 squared, which is going to give 4, plus 4 lots of negative 2. So that is going to give me a total now of negative 4. So the coordinates of the stationary point now is going to give me negative 2, and then we're going to have comma negative 4. What we're now going to do is determine the nature. So we take the second derivative, f double dashed of x. Well, here is my expression for f dashed of x, so we differentiate once more, and that gives 2. 2 is greater than 0, therefore this is going to be a minimum. For now the second derivative to be greater than 0, that means that we have a minimum. So as stated with this, you could have completed the square, and we could have said now that this was going to be x plus 2, and then that would be squared, and then we would subtract 4. So we can see now that if we sketch this parabola, we would have this point now, minimum point, we'd move 2 to the left and 4 down, and it would look something like so. So we would end up with it looking and give or take like that. That's what we're going to end up with, and that point would be negative 2 comma negative 4, and that is a minimum. Let's look at the next one. What I'm going to do is just write this as y is equal to. So we'll look at a slightly different notation. Y is equal to 3x minus, and then we've got 0.5, or if you like, 1/2 x squared. So we can say now for SP, dy dx, so I'm just changing the notation for the practice, will be equal to 0. So dy dx, the gradient function, will be 3, then we'll have now minus x. So 3 minus x will be equal to 0. So we can see from this that the x-coordinate of the stationary point is 3. We can substitute that in now to find the y-coordinate. So y is going to be now 3 times 3, which is going to give me 9. Then we're going to have now minus 1/2 of 9. So what's that going to give me? That's going to give me 9 over 2. So y is going to be equal to 9 over 2. So the coordinates of a stationary point, we're going to have now 3, 9 over 2. So that is my stationary point just there. We can determine the nature by taking the second derivative, d2y by dx squared. Differentiating this expression, we're simply going to get 0 minus 1, which is going to give me negative 1. We can say that d2y by dx squared in this case is going to be less than 0, therefore this is going to be a maximum point. And we saw that requirement or condition in the last video. And if you think about this now, this is simply a quadratic equation with a negative x squared term, so the parabola is going to be opening downwards, and that's why we have a maximum instead of a minimum. Okay, let's look at the next one. In question C, f of x is equal to 2x cubed plus 3x squared minus 72x. This is a cubic equation. So I'm not going to, well, I will write it, because I'll just do this for the first few. For SP, we can say now that f dashed of x will be equal to 0. So f dashed of x, differentiating, we're going to have now 6x squared, so 6x squared plus 6x, then subtract 72. 0 is equal to 6x squared plus 6x minus the 72. We can divide through by 6, so what are we going to have? X squared plus x minus 12. This factors, we'll have now x plus 4 and x minus 3. And then that's going to give us now that x is equal to negative 4, or we're going to have now x is equal to positive 3. Just consider what we've got here. We have a cubic equation. It's a positive cubic equation, and we've seen from our work with cubic equations that if it's positive, it starts in the third quadrant. This one is going to come round and go through the origin, as we don't have a constant, and then it will turn round and come back through. So what we've got here now is this point, and this point is where x is going to be equal to negative 4, so x is equal to negative 4, and this point right here is where x is going to be equal to positive 3. What we need to do is find the y-coordinate of each of these, as we need the coordinates of a stationary point. So all I'm going to do is just substitute this into a calculator. So we're going to have negative 4, and then I'll just plug it in. So 2 lots of my answer cubed, and then we're going to have now plus 3 lots of my answer squared, and then we're going to have minus 72 lots of my answer, and that gives 208. So the y-coordinate is going to be 208. So this point right here, we can say that that's negative 4, 208. And then with this one right here, we'll just find that one. So we'll substitute in 3. So we'll have now 2 lots of the answer, which we need to cube, plus 3 lots of the answer, which we need to square, minus 72 lots of the answer, and that is going to give us negative 135. So y is equal to negative 135, and that point will be just here. So that's 3, negative 135. Clearly, we can see that this one right here is going to be a maximum, and often we call that now a local maximum. This one right here, we can quite clearly see, is going to be a minimum. We've got now positive, positive, positive 0, negative, negative, negative. With this one, we've got now negative, 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 0, positive, positive, positive. Let's go ahead though and just check these. So we'll consider this one, and we also need to consider this one. So with a cubic equation, we've got up to 2 stationary points to find. So what I'm going to do is take the second derivative, f double dashed of x. So if I look now at f dashed of x, here is my expression. So f double dashed of x will be 12x plus 6. What we need to do at this stage is do f double dash of negative 4, because we can see we've got x in here. When we have the quadratic, it simply gave us a constant, i.e. a number. But what we need to do is f double dash of negative 4. So what's that going to give? Negative 48 plus 6, which is negative 42. And we can say that is a max, as it's now less than 0. With this one, if we do f double dashed of positive 3, we can see that's going to give us now 12 lots of 3, which is 36, plus the 6, which is going to give us positive 42. Therefore, it's going to be a minimum. And you might want to make some reference to now that because the second derivative is less than 0, it's a maximum. If it's greater than 0, it's a minimum. I would write that in there. We can see that graphically, and hopefully that's helped out with that cubic function. Okay, let's look at the next one. F of x, I'll do this again as y is equal to, just to vary this up. So y is equal to x cubed minus 3x squared. So with this one, what we're going to have then is dy dx will be equal to 0 for now the stationary point. So dy dx is going to be equal to 3x squared, so 3x squared minus 6x. 0 is equal to, and I can factor this, 3x is common, that will leave me now x minus 2. That looks good, let's just check that. So we can say that x will be equal to 0, and then we've got now x is equal to 2. So yet again a cubic function just here, and we're going to consider now these particular values. If you'd drawn that up, that would have been a nice one to go ahead and sketch. You could have seen the repeated root. So if you'd factor this, we would have had now x squared and then x minus 3. So from our work before, what we would have seen with this one is the repeated root like so at 0. And we've looked at this on curve sketching, and that's the point here, 3. So all I'm doing is factoring this, and if I set that to 0. So we're expecting this one to be a max, and we're expecting this one to be now a minimum. So if x is 0, then we can find the y coordinate now of that by simply subbing in 0. So y is going to be 0, that's the origin. So this one is going to be 0, 0, if we put that on. And then if we substitute in here 3, we can see on here now we're going to, if we substitute in 2, we're going to see that that is going to give us negative 4. Is that going to give us negative 4? I'll write it down as y is equal to negative 4. That's my mental maths there. So this point is going to be 2, negative 4. I'm hoping I've substituted that in. So what's that? 8 minus 12, which is negative 4. Okay, so let's just, we're going to check these now. So taking the second derivative, d2y by dx squared. So if we look at this, this is going to become now, that's 6x minus 6. So 6x minus 6. So we can say now when x is equal to 0, d2y by dx squared is equal to 6 times 0 minus 6, negative 6. We can say negative 6 is going to be less than 0, therefore that's a maximum point. We can say now when x is equal to 2, d2y by dx squared is going to be 6 lots of 2, which is going to be 12 minus the 6, and that's going to give me positive 6. 6 is greater than 0, therefore we can say that this is a minimum. And that is done, and we can see that graphically as well. Okay, let's look at the next one. This one right here. Now I'm gonna draw this and see if it gives you any idea of what we're going to get here. So what we've got is x cubed. It was multiplied by 5 or negative 5, and then we added 4. So 3 different transformations to the cubic equation y equals x cubed, and it's going to look something like this. Let's do that. That's what we're going to get. So this point right here is going to be 0, 4. So this is the curve. Now what I'm hoping to show is that that is going to be a point of inflection just here. Okay, so I'm hoping if I find the gradient at that point, then we will end up now with a 0 gradient. So what we've got then is f of x is equal to 4 minus 5x cubed. So f dashed of x will be equal to, and we can have 0, then we can have minus, so it'll be negative, that'll be negative 15x squared. So for SP, so for SP, f dashed of x will be equal to 0. Therefore, we can see now that negative 15x squared is equal to 0, and we can see that x is going to be 0. So, if I plug that in, we can see that it's going to give us the negative 4, just substituting in. So we can say that the stationary point is 0, positive 4. Let's write that in. 0, positive 4, that's just here. What we need to do now is determine the nature. If we take the second derivative, f double dashed of x, then that's going to be equal to negative 30x. We can say f double dashed of the value we're going to put in, which is 0, that's where the stationary point is, the x-coordinate of that is equal to 0. We can say that this is inconclusive at the moment, inconclusive. Now, in terms of whether it's a max or min, we need to do further investigation. F triple dashed of x is going to be now the derivative of this, which is negative 30. We can say f triple dashed of x is not equal to 0, therefore now it's a point of inflection. So point of inflection. So that's what we end up with. So nice and straightforward, and that's how we've done it. Okay, now let's look at another way that we could have tested this point. If I take an x-coordinate just now to the left, and I'll take now negative 0.1, and I take now a point just to the right of the stationary point where x is going to be 0.1, and I evaluate the gradient. If this now is a point of inflection, when I put it through here, we should get now the same sign. So let's just look at this. So if we do f dashed of negative 0.1, well, that's going to give me now on here negative 15/100. I mean, we could simplify that if I want. All I'm doing is putting this value for the gradient function. If I did f dashed of 0.1, so I'm evaluating the gradient. This is a gradient function, remember. I'm evaluating the gradient at positive 0.1. Well, same thing, we're going to get negative 15/100. Again, we can simplify dividing by 5. So that's at negative 3/20. We can see that the gradient to the left is negative. We have a 0 gradient at the stationary point, and the gradient is negative to the right. Therefore, point of inflection. Right, let's do the next one. So the next one, we got f of x is equal to 16x plus x to the negative 2, where x cannot be equal to 0. So let's find f dashed of x. F dashed of x is going to be 16, and then we're going to have minus 2x to the negative 3. So we can say 0 is equal to 16 minus, so I'm going to just write this as 2 over x cubed. So what we need to do is solve this equation. So all I'm going to do is write now that this is going to be 2 over x cubed. I could have divided both sides by 2. It's entirely up to you at this stage. Multiplying it by x cubed, dividing by 16, we'll get 1 over 8 is equal to x cubed. Taking the cube root, we can see now that 1/2 is x. So x is 1/2. Right, so all I need to do is put this back through to find y. So we can say now that f of 1/2, which will give us y, well, that's going to give me 16 lots of a half, which is going to give 8, plus 1 over this quantity, which we need to square. So that's 1 over 1/4. So that is going to give us 12. That looks right. 1/2, 12. So that's the stationary point. If you wanted to, let's just put that in a calculator. So we found that it's going to be now 1/2 or 0.5. So that's the x-coordinate. So let's just substitute in and check that I've done that. So 16 lots of the answer, plus now the answer to the power now of negative, let's just change that to 2, negative 2. There we go, 12. So that now gives us the coordinates of a stationary point. What we need to do is determine the nature. So we've got an expression for f dashed of x. What we need is f double dashed of x. Now, let's just write it down here. So what we got then is f dashed of x is going to be equal to 16. Then we've got now minus for 2x to the negative 3. So if we do f double dashed of x, this is going to be, for 16 will be 0. That's going to give us now plus. So we'll have 6, then we'll have 6x to the power of negative 4. So if we do f double dashed of 1/2, we can do that now. So that's going to be 6, and then that's going to be 1 over 1/16, which is certainly going to give us a positive quantity. We can say that f double dashed of 1/2 is greater than 0, therefore we've got now a minimum. So nice and logical. Let's just look at that graphically. Let's what have we got? Y is equal to 16x. So y is equal to 16x plus now x to the power of negative 2. Right, let's see if we can scroll out. So here we go. So it's undefined for 0, can't have division by 0, and we can see now that this point right here is the minimum point. So that's our minimum point, and nice and logical and nice and straightforward. So I've just graphed it up, and that's exactly what we've come to find with our work with differentiation. Okay, let's look at the last one. So with the last one, question G, f of x is equal to px squared minus qx. Q is greater than 0 and p is less than 0. Okay, so let's now just put f dashed of x will be equal to 0 for a stationary point. Again, this is a quadratic in x. It's a function of x, so you could complete the square if you wanted. Entirely up to you. So if I write f dashed of x is going to be 2, and then we're going to have 2px minus q. So 0 is equal to 2px, so 2px and then minus q. So x is going to be equal to q over 2p. So that gives us the x-coordinate. Now the y-coordinate is going to be a bit messy. So for y-coordinate, we simply need to sub this in. So what we're going to have is p, then we're going to have now this coordinate squared, so q squared over 4p squared. Then we're going to have minus q, and then we're going to have this coordinate right here. So we need to substitute that in. So that's going to be q over 2p. So let's just tidy this up. So the y-coordinate is going to be now q squared over 4p minus q squared over 2p. So just looking at that, the y-coordinate, it looks like it's going to be now on here. What are we going to have? Q squared over 2 over 4p, q squared over 4p. That, let's just check I've got all of that in there. So 2px minus q, q is equal to, x is equal to q over 2p. Substituting that in, if we square that, q squared over 4p squared, that looks okay. So there we go. That's what we've got. Right. Now, in terms of determining the nature, so that's the x-coordinate, and that's the y-coordinate. So if you want to write that the SP, so SP, I'm pretty comfortable with that. Hopefully it's hopefully I've simplified it correctly. Q squared over 4p. So that's what we end up with. Okay, now with this, we could take the second derivative if we want. If we just consider what we're going to get now, f double dash of x is simply going to be now equal to 2p. Remember, this is a function of x, so the derivative of 2px is just 2p. Derivative of negative q is just going to give us 0. So f double dashed of x is 2p. We know that p is going to be less than 0. Therefore, we can say that f double dashed of x is going to be now less than 0. Therefore, this is going to be a maximum. Alternatively, if you just consider that this is a quadratic with p here, p is less than 0, so the parabola would open downwards. So, for example, if p was equal to -3, we could see -3x squared and then any value for q. That's what we would end up with. So it's a maximum. So lots of different approaches with that. So there we go. There's some basic work now looking at finding stationary points and determining the nature of them. In the next video, we'll do some more questions on stationary points and looking at their nature.